Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm really happy to have Rachit Agarwal here today. So Rachit is now a postdoc at UC Berkeley working with Ion Stoica. He did his PhD at UIUC with Brenton Godfrey, and Rachit works on distributed data-intensive systems, in particular these storage systems that can answer very sophisticated and cool queries, even over compressed data, which we're going to hear about today. The thing that I like the most about Rachit is that he publishes both in systems conferences like NSCI and top theory conferences as well, like SODA. So he really is kind of a bridging force between the systems and theory communities. He's also received several awards for his research, and I'm looking forward to hearing his talk today.
Perfect. Thanks, Sid, and thanks for having me here. Thank you all for coming to the talk. I'm very happy to be here. So my research, yes, like Sid said, a lot of interesting stuff happens at the intersection of systems and theory, and hopefully I'll give you some picture about the theory side. But this talk is going to be slightly more on the system side, because I think some of the interesting stuff here might actually excite you. So I started my postdoc at UC Berkeley 2 years ago, and at that time we were trying to understand what are the trends that are coming out of hardware and applications that people want to run today. And one of the trends that has really stood out and that we have been hearing more and more over the last couple of years is Moore's Law. Hardware designs not being able to compete or keep up with the Moore's Law. And on the application side, there's a very different trend, which is the data sizes are becoming larger and larger, and in particular, data sizes are growing faster than Moore's Law. So there was this mismatch between what people were trying to do or the kind of data sizes that people were trying to deal with and with the hardware that people use today. And that's how this project Succinct came up, and I'll talk more about motivation. But the main goal in this project was to understand, is it possible to take a server with, say, 64 gigabytes of RAM and push up half a terabyte of data, or 128 gigabytes or 256 gigabytes of data in the main RAM and do computations as if we do today. And the basic question was formulated as a compression question that I'll talk more about. But the overall talk is going to focus on so-called interactive query systems. And I'll define what interactivity means, but for now, think about when you interact with Facebook or Twitter. The kind of interaction you're having between you as a user and the web service. That's what I'm going to call interactive systems. And the first realization was that these trends that I'm going to talk more about lead to this problem that query interactivity is getting really, really hard to achieve, even in today's systems. And there are two main reasons for that. The first one is scale. The last few years, we have seen that the rise of social media has given us access to this tremendously large amounts of data that people are trying to exploit in many, many interesting ways. In particular, terabytes of semi-structured data is now quite a bit of norm. Actually, if you talk to any small company as well in the Bay Area, they talk about tens of terabytes of data, right? Large companies are talking about hundreds of terabytes or petabytes of data. But the important thing, like I said, is that data is growing faster than the Moore's Law. Okay, so people are really trying to do very, very interesting things on this massive amounts of data. It's not just the scale of the data that has increased. People still want to do complex queries. For example, here I have a collection of tweets. Twitter last year announced that now you can actually go and search across all these set of tweets. So each tweet has some user ID, some timestamp when the tweet was created, and some text. And people may want to search for tweets that mention certain spaces or certain name, right? Similarly, Succinct in itself had one initial interesting question about that came us with one of the large publishers that we work with, which is that they had this large collection of documents and they wanted to do very fast regular expression queries on this massive collection of documents, hundreds of terabytes of documents. And they use these regular expressions in an interesting way, right? So these are user-facing queries. When users go to this publisher's website, they actually run these regular expressions in the background. And then every time you go to Facebook, Facebook internally does something which is called a range query, and I'll define this as well. And essentially what it says is, tell me all the posts that have been generated or all the likes that have been generated within certain two time ranges. So it's a range query. So people are trying to do all these complex queries on this large scale of data, right? But it's not just the scale and the complexity. One thing that has remained unchanged over over the last few years is that the definition of interactivity as a user, if anything, we are growing more impatient, right? We close up a website if it doesn't load up in a few hundreds of milliseconds. So the definition of interactivity that I'm going to use in this talk, which is slightly vague, but basically what I'm going to say is that we need low latency, so tens of milliseconds, essentially. And as long as that latency is less than a certain bound, we are going to want high throughput, which is the number of queries that can be answered by the system per second. Okay? Okay. So the three challenges now: scale, complex queries, and interactivity. And there's been a lot of work at the intersection for looking at these challenges either in pair or in isolation. And of course, scale is, we have studied scalable algorithms for a long time, how to do complex queries and things like that. But if you look at the intersection of these three, we have this new bunch of very interesting problems that some people refer to as interactive big data problems that are both high impact and very, very challenging. And I'll talk about the challenges. My research essentially focuses at this intersection of these three constraints. This space of the intersection of these three constraints is also a space where existing systems start to fail. So let me start with a very simple experiment and show you some numbers. So suppose I have these search queries on this collection of, so the Conviva is one of the companies that generates these video logs. This serves online videos, and every time a customer comes to the website, they generate this kind of log where each record has a record ID, who is the user, when the user starts seeing the video, when the video ended, and some of the tags for the videos. And I'm going to run these search queries on these columns. So each of the search query is essentially a query on one of the columns. And I'm going to use a single Amazon EC2 server with a single core and some 60 GB RAM. So let's look at what happens. On the x-axis, what I'm going to do is I'm going to increase the amount of data that I'm going to push on the server, right? So varying from 1 GB to 128 GB. On the y-axis, I have the number of queries, so search throughput, that is the number of queries that is answered by these systems. And I'm going to look at these three state-of-the-art systems for this space. So for Elasticsearch, as we scale up the data sizes, this is what the performance looks like. Okay. So for small data sizes, the performance is more or less stable at roughly 200 queries per second, which is roughly speaking 5 milliseconds. And then suddenly the performance drops beyond 16 GB of data. Okay. And this is not just Elasticsearch. If we look at MongoDB, we see a very similar trend, right? And with Cassandra, a very similar trend. So as soon as you look at this result, you actually one asks, what is happening in this space? I have 60 GB RAM, and I can't do anything more than 16 GB, anything interesting more than 16 GB, right? So what is actually happening in this space? Any guesses? Swapping, exactly. So what happens is things start running out of memory, right? And I'll talk more about why it's happening at 16 GB. But essentially, a lot of people have realized this, that if you want to achieve query interactivity, you have to do queries in memory, right? In-memory query execution is the key. In particular, if you look at hardware trends, today secondary storage, which is SSDs, is 100x slower than main memory. And a very simple calculation shows that even if 10% of your queries go to secondary storage, your system answers 10x fewer queries, actually 11x fewer queries. In fact, even if 1% of your queries go to secondary storage, your system answers 2x fewer queries. Yes?
Is that SSD backed or is that a hard drive?
SSD backed.
Okay.
Yeah. So hard drives are thousands of times slower than main memory. So these numbers would look even worse. So, and nobody's using hard drives today. So secondary storage, SSD backed, this is what your performance numbers would look like. Even if 10% of the queries were going to secondary storage, you will see 11x performance degradation, which is essentially what is happening here. Yes, Sally.
So, and all of this is for, I imagine, answering the queries exactly, so there is no approximation happening here.
Yeah, right now we are not doing any approximation. These are exact search queries or range queries. Yeah. Okay. So the question is, what do we do about this? essentially, this is what my research focuses on. My research, in particular, looks at bridging the gap between the memory capacities that we have in today's systems and the data sizes for which we can interactively query using these memory capacities. In particular, the functionality that we focus on, we say that, okay, we want to get the state-of-the-art functionality of state-of-the-art NoSQL stores, and we want to bridge the gap. So coming back to this curve, what we are essentially looking for is whether there exists a system that can achieve a performance like this. So let me try and explain this more. What we want is, we say that, okay, when the data sizes are small, of course, we are getting close to optimal or close to good performance, but we want to maintain the performance for a much larger range of input data sizes. At some point, your system will run out of memory and your performance will drop, but this is the range that you want to get gains for. And x-axis is log scale here, so we are actually asking for a lot, okay? Question is whether there exists a system that can achieve this new curve. If possible, clearly the gains will come out of the fact that we can do in-memory query execution for larger fraction of queries. And if you look at performance at scale, we'll get multiple orders of magnitude faster performance. Okay. The question is that system exists. So this particular project, Succinct, is essentially trying to solve this problem. It's a distributed data store, which means it's storing data distributed across multiple servers. Essentially, what it does is, suppose this is your input data, and I have color encoded. I'm going to use this example throughout the talk. I have the color encoded the file here. Each of the blocks here could be a term or could be a substring. It could be a collection of characters. Right now, think of it as an ASCII file set. Okay. And then I have multiple blocks in the file. What Succinct does, it takes your input file and it transforms this file into a suite of data structures. Okay. There are two interesting things here. The first thing is that these suite of data structures are a compressed representation of your input file, which means if these suite of data structures will have size no more than your input file size. This is guaranteed, right? And the second important thing is that Succinct does not store the input file. All Succinct stores is this compressed suite of data representation. Okay. But now that you have this suite of data structures, you can execute. So basically, it's a compressed data store. But once you have this suite of data structures, Succinct allows to execute a lot of powerful queries directly on this compressed data set. Okay. So question is, what happens to the three problems that I started the talk with? The first thing is that Succinct allows you to do very complex queries directly on this compressed representation. In particular, you can actually search on the file without scanning the entire file. So you can actually provide you the functionality of indexes. You can do range queries. You can do random access. And actually, you can even execute regular expression queries directly on this compressed data. Okay. On the other two sides, since your data structures that Succinct stores is no larger than the input data size, you have now that the amount of data in memory is at least as large as the memory capacity, but usually the real-world data is very compressible, so you get a lot of gains there. Okay? And finally, Succinct does not require doing data decompression or data scans, so we get interactivity. Okay. So in this space, we have had a lot of interesting work done over the last 2 years. We wrote this original Succinct paper. We showed how to do queries on compressed data in NSTI 2015. This year, we showed that the ability to be able to do queries on compressed data actually allows you to look at a lot of classical systems problems with a new perspective, and you get a lot of interesting new solutions. This was a paper in NSTI this year. We have a paper in submission where we showed how to do regular expression queries on compressed data. And more recently, I've gotten very interested in the security side, and we are trying to understand if we can do queries on compressed and encrypted data. I'll talk more about it later. But a very preliminary paper that we wrote, it actually allows you to build a key value store. It doesn't support complex queries, but now you get compression and encryption. While we were doing this academic work, we did not shy away from real-world impact. Succinct is already being used in real-world production clusters for large-scale web services today that I think every one of us interacts with every day. In particular, Elsevier and one of the large publishers is starting to use Succinct. And Succinct is also into the main code of two startups, which is Databricks and Tachyon. So this is what we have been working on for the last 2 years. Today, I'm going to focus on the first two projects because I think they really show up my usual approach to solving problems, which is.
So I just had a couple questions about the setup. So you're doing compression, but you're doing lossless compression, correct?
Yes.
And when you say it's no more than a factor of 1 worse than it was originally, you mean a factor of 1 plus some tiny epsilon?
So I'll get more into that, the second question. The first one, yes, it's lossless. Everything I'm going to talk about is exact solutions, so it's lossless compression. The second one is, imagine that we take the input file, and suppose the input file is not compressible, right? So then you get no compression. But essentially, what will happen is you still get the functionality of so-called indexes, right, which people today use in addition to your input data, right? So if you fix the functionality, you get a huge compression still. You're not compressing the input file, but you get huge compression, right? If you fix.
You said random access, so you have to be lossless, right?
Yeah, it's lossless.
Okay.
Everything is lossless. It's random access. All the functionalities that I talked about, you get it on data sizes no larger than your input data size in terms of your input size.
If somebody gives you a file full of random bits, then you're going to have to require a little bit of extra beyond that in order to handle it, right?
It's slightly non-intuitive, but yes, you're right. There are some little ON terms, but in practice, yeah, it could be an epsilon. But as you increase the data sizes, I think that epsilon is just going to vanish away. In practice, however, if you think about the Facebook data or Google data, right, we see very, very high compressibility. So even the numbers today that I'm going to show you later in the talk, they're for very conservative data sets where we get little or very little compression. Over there as well, you get 3x, 4x compression easily, but you get the functionality of indexes, which are usually 4x larger than the input data sizes.
Yeah.
So it's.
So you're going to be reusing the way the compression algorithms work to do indexing. Right? I mean, compression algorithms actually build an index. Like lensGFE builds an index as it's running.
Yeah, so what I'm going to show you today is a different way of doing compression. I'm not going to work with lensGFE. I think there has been some follow-up work on how to extend lensGFE to do our kind of analysis as well in last year or 2 years ago. But yes, today I'm going to show you a different way of thinking about compression completely. Okay, so usually my approach to solving these problems is twofold. The first one is most of the times, the problems that I have worked on during my PhD thesis and during my postdoc, I have always been motivated by real-world problems. But it's not just the problems. I've also focused a lot on the system resources, on what kind of constraints arise from today's hardware. So looking at these two from two perspectives. The first one is taking these problems and the system resources and designing scalable algorithms and techniques. That is usually the first step in my research. Once we have a scalable algorithms and techniques, then I build these techniques into scalable systems. And I really want to emphasize this fact, which is I think different about my research, is I truly believe that it is very important to look at these two perspectives to solve these problems that we are facing today. If we were to focus only on system side, then we will fail to leverage the structure in these very specific kind of problems that we are trying to solve. On the other hand, if we were to focus only on algorithms and techniques, and I have done that in the past, we are going to ignore some of the advances that come out of system design. So I truly believe that it is very important to look at this problem space from both systems and algorithms perspective. Coming back to research, I want to start now, dive a little deeper and actually look at this problem that I initially talked about and try to give you some idea whether this is actually a fundamental problem or is it just that these systems are poorly designed. Because if this problem is not fundamental, it's not probably worth solving. So how do people do today? How do people do search today? Where is that curve coming from? So they're essentially, let's look at the same example. Suppose I have this file and I want to search for the green blocks. Okay, there are essentially two techniques that are known today to solve this problem. The first one is so-called data scans. The nice thing is, in terms of data scans, you store your input data in memory, right? Hopefully, and when a query comes in, you actually scan the entire file. it's not just the animation. The data scans are actually that slow. Okay. So, but the nice thing is that you have to store only your input data, and hence you have low storage. But since you have to scan the entire file for each and every query, you get low throughput, right? On the other hand, people in the database community have done this very large amount of work over the last decade or 2 decades, where they have built so-called indexes. So how do those work? You store your input data for random access. In addition, you pre-process your input data to create a suite of data structures, right? Here I'm showing a standard inverted index where for each of the colored objects or the possible queries, you have already pre-computed the results and stored them, right? What is the nice thing? The nice thing is whenever a query comes in, you do a binary search on your index and you get your result, right? What is the bad thing? The bad thing is that you have to store these data structures in addition to your input file, and sometimes they can be large, so you have high storage. Okay, so that curve dropping thing was happening because of this high storage. Let's see how. So the same plot where I have data sizes increasing on the x-axis and search throughput on the y-axis. This is what the data scan performance looks like for one of the state-of-the-art databases that do very fast data scans. Essentially what is happening is you have data in memory, but your scan latency is increasing linearly as the data sizes increase, right? At some point you run out of memory and things look bad. So scans in faster storage and slower storage. And this is the curve originally that I showed you with Elasticsearch. What is happening over here is when indexes are in faster storage, you get really good performance. But since indexes have some high storage overhead, they start running out of memory after 16 gigabytes of data, and you start seeing this performance drop. Okay, so this is actually a fundamental problem. Yes.
So that separation of indexing and storing database community. So like things like bin trees combine the two of them. So how does that? I mean, it's not really high storage and indexing. It's the two of them together, right? Like the index is part of how you store things.
Oh yes, absolutely. So the way I was suggesting was that you have to store some data structures in addition to your input data. So B trees will, as we know about B trees have a storage footprint which is 1 plus some alpha in terms of your input file size, right? So I was talking about that there has to be this 1 plus alpha part, while Succinct is trying to do, no more than 1. Okay. So this is what you pay for executing queries of slower storage. So what Succinct does, like I said earlier, it takes your file, it compresses it down to this suite of data structures, and now you can execute queries directly on this compressed data. And what I want to convince you, basically, essentially, is that you can get low storage and high throughput, okay, for a lot of interesting workloads. And why is this interesting? Because Succinct does not have to use secondary indexes, which are actually a pain for different reasons as well. Without Succinct using secondary indexes, Succinct actually gives you the performance of indexes. So essentially, the data structures that I'm going to talk about in next few slides are going to show how we actually embed the indexing information within the compressed representation. Okay, so we don't have to do data scans. Unless you actually want to read your original data or do data access, we don't have to do data decompression. Okay. So getting back to this curve, here's what Succinct performance looks like. This is the real analysis. Now, the left part is not fundamental. Okay, Succinct does not have some. It's a very early stage system, so it does not have some of the overheads that other systems have. Plus, it's written in C++. Plus, we have spent a lot of time optimizing it. So that part is not fundamental, but this part is actually fundamental. Okay, so we roughly get 8x larger data sizes in memory compared to today's systems, and usually much more. And in fact, on a 60 gigabyte RAM server, we are able to push more than 128 gigabytes of data and execute everything in sub-milliseconds. Okay, so we are actually giving you more than the server capacity, an illusion of having much more RAM than what is available today. Okay.
So at 256, presumably it drops down to.
Yeah, I'll show you later on, yes. Yeah, it's slightly non-intuitive, but I'll show you why it's happening at 256. Okay, good. So now let me dive a little deeper and show you what Succinct can actually do and what is the data model and functionality. So when we started building Succinct, we had a big question in front of us. What kind of data models did we want to support? Did we want to work with documents or small key value pairs, large key value pairs? And we decided that we were going to support only flat unstructured files. And this is this is a 15-year taking a step back and going into how we used to do things 15 years ago. But I'm going to show you some very nice, simple result later on why this flat files is such a powerful interface for today's systems. But once you have this flat files, which is on the left hand, on the right hand, Succinct computes these data structures, and now you can execute the following queries. So, like I said, you can search. So, search query will tell you the corresponding offsets in the flat file. Okay. You can actually, one of the important things I think I should mention is that the search is not term aligned. You can search for arbitrary strings in Succinct. Okay. So essentially, you can take any arbitrary part of the file, including dots or any of the delimiters, and actually search in Succinct. You can do random access. So starting at any arbitrary offset in the file, you can read as many bytes as you want. You can do counts. You can do append new data. So Succinct currently does not support in-place updates very efficiently, but you can append and delete data. And then you can do range queries, and like I said, you can do regular expression queries. Okay. So trade-offs. So Succinct does not require secondary indexes. It has compression, so it can keep more data in memory, and we don't have to do data decompression. There must be something that we are missing, right? It's a systems work. There's no free cake. So Succinct does make some very interesting trade-offs that I want to outline very clearly. So what do we lose? I'm going to tell you two kind of trade-offs that Succinct makes. One is more on the fundamental side, and the other one is more that we haven't reached that stage of maturity. But from the fundamental side, Succinct has to spend some time pre-processing the data, compressing the data, right? So in compared to data scans that can answer the queries as soon as you upload the data, Succinct has to spend some time pre-processing the data. So there's that time lost. When you want to do data access, we have to spend some extra CPU cycles in comparison to systems that do not do data compression, obviously. Succinct works with queries that have more random access kind of format, so search and random access and range queries. It's not very useful for systems like MapReduce currently, where you want to read massive amounts of data, like hundreds of megabytes or even gigabytes of data. So sequential scan throughput is low in Succinct. And like I said, in-place updates right now are supported by a delete followed by an append. So we do not support in-place updates very efficiently. On the current limitation side, we have a couple of interesting projects going on where we are looking on supporting transactions and having stronger consistency guarantees on top of Succinct. So Succinct does not provide strong consistency guarantees right now. Okay, so these are the negative sides of Succinct. Okay, so now let me spend next 10 minutes trying to show you how Succinct works. Okay, and this is going to be slightly tricky. Actually, this crowd, this might be easier to show. But one thing I want to take away, I want you to take away from this is that although Succinct looks complicated, the underlying techniques are really simple. Okay, at least the basic part of it. And I want to show you how Succinct does this compression and allows queries on compressed data using such simple techniques. So essentially, it builds upon some of the very old theory work that was done in context of suffix arrays and FM indexes that I'll talk about later on. Succinct has this new data structures that actually allow you to use these the old data structures in a very efficient way. And of course, new query algorithms that allow you to do these powerful queries on compressed data. And I'll talk about these algorithms later on. But let me start with this very simple data structure that we have known for many years in computer science research, I think 45 years now, which is called suffix arrays. Okay, so this is my flat file. Succinct takes input as a flat file, and the numbers on the top of the file are just showing the index into the file. So my character at the 4th index is y. Okay, so how do these suffix arrays work? The first step in this construction of suffix arrays is to actually construct all the suffixes in the file. So since it's a suffix, the entire file becomes the first suffix. Then you remove the first character, and you get the next suffix, and so on. Okay, suffix arrays then sort these suffixes lexicographically. Okay, so you take all the suffixes and you actually sort them lexicographically. Okay. Now, for each of the suffix that we have in sorted order, you store the suffix location in the input file. So for the first suffix, for example, it starts at location 1, which is right here. and you store that location. The second suffix starts at location 0, and so on. Okay? So this part is called the suffix array in traditional literature. I'm just going to abuse the notation and just call this as suffix arrays. Okay? Now, in original literature, of course, as you would imagine, you don't have to store this because you can just store the input file. I'm going to store the suffix, the set of suffixes along with the original suffix array and just represent them here. Okay? So it's the same thing, location of suffixes in sorted order. So why are these two arrays interesting? Because when I want to do a search, for example, I can do arbitrary substring search by binary search. So suppose I want to search for PPY, I will do 2 binary searches to find the first occurrence and the last occurrence of PPY, right? And the lower array will give me the corresponding locations in the input file. Okay? So I have these two arrays that provide me the search functionality. What is the problem? The problem is that the topmost array requires roughly n squared bits, right? And the lowermost array requires roughly n log n bits because this is essentially a pointer into the input file, which is n characters. So you require log n bits. Okay? While your input file, on the other hand, if it's an ASCII file, is just 8n bits. So these two arrays are much, much larger than your input file. So let's see what we can do. Let's focus on the first. So how do we reduce the space? Let's focus on the first two here. Okay? And I'm going to make one simple observation here. The first one, the observation here is that this suffix is obtained by removing the first character of this suffix. Okay? Suppose I can store this pointer, which tells me where the next suffix is stored. Okay? So this tells me that the next suffix is stored at location 0 in this suffix in this array. If I can store this pointer, the nice thing is that I don't have to store this entire suffix. I could just store the first character and then reconstruct the full suffix on the fly. But this pointer is interesting from another reason as well. See, these are the locations of suffixes in the input file. Since I've removed only one character, my value increases by 1, exactly 1, right? Which means this pointer also tells me where the next larger integer in this array is stored. Okay? So I don't even have to store one of these values. I can just store one of the values and compute the other one on the fly. Okay? And I can recurse this over the entire set of suffixes. Okay? So what I'm left with is one character for this n squared bits that I had, some sampled values here on the suffix array, and some set of pointers. Stop me if this is not clear. Okay? And I can compute everything on the fly. But since these characters are sorted, I don't even have to store one per occurrence. I can just store the first occurrence of all the characters and recompute everything on the fly. Okay? So I've taken n squared bits and converted it into less than 1 kilobyte of data for ASCII file sets, some sample values and the pointer values. And these sample values, I can choose a sampling rate such that the size is much, much smaller than the input file. I'm left with this array. Are we on the same page? Okay, good. So this is what Succinct stores. Succinct stores these two, some sampled values and some of the characters, and one set of pointers that allow you to compute the unsampled values on the fly. Yes. Yes, go ahead.
Do you try to use run-length encoding techniques to further compress?
Give me 1 second and then I'll show you. So how to compute unsampled values? Like I said, if you want to compute unsampled values, I have this notion that my pointer tells me where's the next larger value stored. So I start with one of the unsampled values and keep looking up pointers. Every lookup increases my value by 1, which means I have this simple formula where once I find one of the sampled values, I subtract the number of pointers I have looked up and I get my unsampled values. Okay? So I can compute the unsampled values on the fly. So I'm left with this essentially the set of pointers. Now, I must have really joked with you because what I did was I took this massive array with n log n bits and replaced it by another array which is n log n bits, because essentially this is a pointer into an array of length n, right? So each of the pointer values still requires log n bits. But look at this nice structure in the set of pointers. If I look at all the values, all these pointers that start with the same character, they actually constitute an increasing sequence of integers. Okay? And this is an easy proof to show. So essentially, while my suffix arrays to start with did not have any nice structure that allowed me to do compression, I took those suffix arrays, stored a collection of pointers that allow me to recompute those suffix array at any value, and these new set of pointers have a very beautiful mathematical structure. Because these are increasing sequence of integers, I can use traditional encoding techniques like delta encoding or run-length encoding to actually compress this. So I took this problem, which was a completely text-based problem, and reduced it down to a compression algorithm that we have studied for many years, right, which is run-length encoding and delta encoding. Okay. So this can be compressed efficiently, and this is what Succinct stores as well, a compressed representation of this set of pointers. These are very small in practice. Succinct takes another step, actually. So now this is more on the practical side. Succinct transforms this pointer array into a two-dimensional representation. Essentially, what we can guarantee is that each row is not just increasing sequence of integers, but actually contiguous sequence of integers. So you get much better performance. But more than that, this two-dimensional representation allows us to remember when we were doing the binary search on the original array, we still had to do binary search on the entire array, and binary searches are known to be not being cache efficient. So in this two-dimensional representation, we show that you can actually do binary search on a very small subset of the entire array using some very few bits, and hence you get very fast queries. Okay, so we get a lot of benefits from that.
So what is the cost of your first transformation? Is that just additional space?
The transformation cost in terms of,
Did you pay any price for doing that?
yeah, we have to spend more pre-processing time.
Oh, it's just time. It's not.
Yeah. In terms of space, you actually gain in practice, but theoretical bounds do not change. Yeah. Okay, so and Succinct stores another array like this, another sampled array for random access. So till now I just talked about search, but you also have to do this for random access. Okay. Okay, so this is all Succinct stores literally. This is just the entire Succinct technique really, except for some details. Okay, so if I look at the storage versus throughput curve, we started at this point. Indexes had very high storage, but were also very high throughput. Scans were somewhere here where you had lower storage but also low throughput, and we have a better point than scans now that we have Succinct. Okay. So coming back to, it's the same results that I showed you earlier, basically, but now with slight more intuition. All these systems, if I start doing it for these data set sizes, beyond 16, all of these systems run out of memory, and hence you are seeing that drop, right? Succinct goes all the way until 128, where things can be kept in memory. The interesting thing here is that we can completely back up the numbers, performance numbers that we see in particular. At 64 gigabyte RAM sizes, this system Elasticsearch is actually executing 44% of the queries in memory. That's it, right? So you would expect a performance degradation of roughly 55% or 57%, 57x. And this is what we see essentially in the numbers here, that you see roughly 57x performance degradation, and your queries get down to 1 query per second. Okay, so we can literally back up the performance of these systems using a very simple analysis in terms of how many queries are actually going to SSDs. And this is what Succinct performance looks like. At 256, Succinct does run out of memory on this server, and the performance drops. Okay. Okay.
Tank as much as I expected, though.
Sorry.
Does not tank as much as I expected, though.
There's not much drop, you mean?
Yeah, I expected more drop.
It's an order of magnitude, roughly speaking.
Yeah, I understand.
The-
but I would have expected it to perhaps even work worse than a scan, because SSD is reasonably good at scanning compared to random access.
Yeah, I think the reason is that we still, until 244 gigabytes, we were still in memory, I think. So we had 10% of the queries going to SSDs, and that's how you see that much drop. So, yeah.
But if you completely exceed RAM,
Then we are going to
do you
fall off.
actually work worse than
Yeah,
scan?
but it's just that you can't go below 0, which other systems have already reached. So, but yeah.
0 or 1?
Yeah, I think over here these just stop answering. It takes tens of seconds to answer these queries. But yes, you're right that there is a certain data set size where I can make other systems that are doing scans work faster than Succinct if I were to be in memory, in disk. The gains that you get are really for this range until Succinct completely runs out of memory. Okay. So we see very similar patterns for random access as well. It's just that the drop for other systems is much lower because you don't have to do binary search on SSDs anymore. You have to just go once to SSDs, and hence the drop is much less significant. And you see roughly similar performance in Succinct, but again, the performance drop is much lower. So how do we take this technique and turn it into a distributed data store? Like I said, you have to think about multiple things in terms of data model. How do we do sharding and replication? How do we do updates? How do we handle skewed workloads, transient failures, and so on? So I'm going to focus more on these three, which is what data model Succinct supports, and skewed workloads and transient failures, because that's where I think one of the cool things about Succinct is. Let's start with the data model. So existing systems essentially make a very hard trade-off of supporting one of the written data models there. So either they support unstructured data, key value stores, documents, or tables. In Succinct, we decided that we want to go with flat and structured files, and it turns out that using these flat and structured files, we can actually build a unified interface to support unstructured data and key value stores and document stores and tables. So we can actually support, and actually some more recently. So we can actually support all these different data models using one single system. And let me show you how do we do that. So this is Succinct interface. The user works with the system as if they were working with any other system that supports their interested data model. For example, here I have a table that has 4 columns. Okay? So user submits that table to Succinct as if it was submitting a table. Succinct internally takes this table and assigns each column a unique delimiter. Okay? And then it writes it down into a flat file. For example, for the first column, it takes each of the values and appends the delimiter and writes it down into a flat file. Okay? And then it does the same for each of the columns. And once I have this flat file, I construct Succinct data structures on top of it. Okay? Oh, so the green column, in the green object in the first column, and the corresponding delimiter is the first left, on the top left. Yes. Actually, it doesn't matter, but yes, all that matters is the value followed by the delimiter. So you, but yes, you can read left, right, bottom. Yes. The interesting thing is that once I've written down this table as a flat file, if a query comes in and says, find me all the green blocks in column 1, internally Succinct transforms this query into the green block followed by the corresponding delimiter of column 1. And it is very easy to see that the results will be equivalent for the 2 queries because of the delimiters. And since I can do tables, I can do key value stores, I can do documents, I can do multiple JSONs and everything, right, using this simple transformation on flat files. Okay. So let me now talk a little bit about the 2 different kind of workloads, skewed workloads and transient failures. And I think this is one of the cool things I want to show you about Succinct. So Succinct, as I said, is stored for this input file. Succinct stores some small number of bytes, another small array, and then 2 sampled arrays. Okay? So these are really small, and the other 2 sampled arrays actually decide on Succinct's storage. In particular, if I use some sampling rate x, then storage is roughly defined as 2n log n, because each of those arrays had n log n space requirements, divided by the number of samples that you're storing, sampling rate. And once you want to compute unsampled values, then you have to take those many pointer lookups. So latency roughly grows linearly with the sampling rate. Okay, so can I build something nicer other than just doing replication and doing some things which people use today? So let's see how do we store these sampled arrays. And this part of the talk is motivated by something that we did long, long ago in video encoding literatures, which is called multi-layer encoding. Okay, in particular, suppose I have this sampled array where I'm storing every second value. Okay, rather than storing the sampled layer as a collection of every second value, what Succinct does is actually stores this as a collection of different layers. Okay, let me describe what each layer is doing. So for example, for this example case of sampling rate being 2, the topmost layer here is storing rate 8, so every 8th sampled value. The second layer is storing values of rate 4, so every 4th sampled value except for those that were stored in the top layer, right? and then in RAID 2, every second value except for those that were stored in the upper layers. So I've taken a sampled array and stored it along multiple layers, right? Why is this interesting? The interesting thing here is that suppose I want to delete a layer. Suppose I delete a layer with RAID 2, right? If I delete this layer, suddenly I've changed my sampling rate from 2 to 4. Yes? It's very simple, just as memory deallocation. I've changed my sampling rate from 2 to 4. I have lower storage, but higher latency. Okay? Suppose I want to add layer now. Remember, Succinct is computing unsampled values on the fly. It's a lossless compression technique, right? Suppose I want to change my sampling rate from 4 to 2. I add a new layer. So my sampling rate changes from 4 to 2, but these are the systems that are answering user queries. So I don't want to spend extra resources filling in values in this newly added layer. But Succinct is computing these values, some of these unsampled values on the fly. So I can opportunistically use some of the values that are computed to fill in this new layer. Okay, so I essentially get a very low cost, low overhead way to populate these new layers and changing the rates on the fly. So coming back to, in fact, just storing a few extra bits, I can actually guarantee that the layer addition and deletion is independent of existing layers in the system, and actually query execution is also independent of existing layers. So why is this interesting? The interesting thing is that, remember this plot I showed you with the indexes and Succinct? What this trade-off, what this layer addition and deletion allows you to do is, rather than achieving one single point on this curve, you can actually achieve any of the points. So it actually allows you to achieve something that we have never been able to achieve in distributed systems, which is a smooth trade-off between storage and performance. In fact, by adding and deleting these layers on the fly, Succinct actually allows you to move along this trade-off curve in a very efficient manner. Okay? Because now you can add and delete storage, and depending on the performance, you can actually change your storage on the performance requirements. Okay?
But do you actually reach the point where you're equivalent to a scan? I don't think you do.
It's actually better than scans. You can always do better than scans in Succinct unless everything is happening on SSDs.
Right.
Because you are Pareto optimal compared to scans, right? So, but yes, we do reach point where you meet indexes.
So a scan has, so if you have an incompressible file, then all the extra data structures that you require are just extra RAM usage.
Yes, which would be very small. Yes.
It would be small, but it would still be just extra, and then you would presumably would not be able to compete with the scan.
Oh, for most of the queries you will still be able to, because still it's an index kind of structure, right? So for most of the queries you will still be able to answer queries off memory. That extra space might actually go to secondary storage, but that will be a very small fraction.
So let's see. So when it's just load the file or download the file, then you would not be able to with the scan. But any kind of search you can.
Right, right. Or random access.
Yeah.
If you want to read the entire file, yes, sure. Data scans will be faster. Okay. So essentially, what this adding and deleting layers in Succinct allows you to do is take a system like this, where I have one server, I have 3 shards or 3 partitions on the server, and suppose the first shard has a lot of requests, the second shard has very few requests, and the third one is somewhere in the middle. What Succinct, this different layers allow you to do is actually transform the system state into another system state, where the heavily loaded shards can have higher storage and hence higher performance, and lower loaded shards can have lower storage and hence lower performance. Okay? And hence you can have a very balanced state. Okay, so let's apply this idea. Actually, okay, so essentially what Succinct allows you to do is increase and decrease the storage fractionally, okay, and just enough to meet the performance goals. But this raises a lot of interesting questions that given the load, how should different shards share available cache on a server and across servers? How should you schedule queries across shard replicas and so on, right? In this NSTI paper, we had this very simple, cute result where we showed that empirically speaking, shards are able to share the cache proportional to the respective load, which is ideal scenario, right? The available system cache. But more interestingly, you can do it without any explicit coordination. Okay, so the system did not require to explicitly coordinate between machines to be able to achieve this very nice property. And the intuition is that we use a back pressure stylus scheduling mechanism that actually allows you to schedule queries while achieving this load balancing problem. But an interesting problem in this space, at least I'm trying to understand, is if we can build any analytical understanding of whether it's actually just an experimental artifact or you can actually prove things about this cache proportional to respective loads.
So there are limits, though, to how far this approach can go, right? Because if all the queries are for one of your end files, then that one file is sitting on one server, right?
You can have replicas. In this case, you can have shard replicas. So those replicas on different machines will grow larger.
The system does replicas?
Yeah, system just, yeah, I did not have time to talk about. We are doing a standard replication, yeah.
It won't do like dynamic, it's not going to elastically replicate, but you can maybe, augment it to do something like that.
Right, you can have replicas, multiple replicas sitting on SSDs, and load balancer will take care of which replicas need to be in memory and how much storage they need to have or how much cache space they need to use.
But it's not doing on-demand replication.
No, right now we have not. Yes, right now we have not implemented on-demand replication. Okay, but I want to show you the application of this idea into two cases. Where the first case, like I said, people talk about this all the time in systems literature. Where suppose you have multiple shards. So on the x-axis I have the shard IDs. On the y-axis I'm showing the load on the shard. Right. The state-of-the-art solution today is so-called selective replication, where what people do is create as many replicas for the shard as the load demands. Okay. Essentially, what this idea gives you is a coarse-grained control over the throughput that the shard can support. So you can create one additional replica and you will get 1x throughput increase. What Succinct allows you to do is move along this trade-off curve and get fractional increase. So intuitively, it actually allows you to increase and decrease the storage rather than always in 1x granularity, but it actually allows you to increase and decrease the storage fractionally. And this is what you would assume we would get is we can, even in the worst case scenario, what we have seen is 1.5x higher throughput than selective replication. So this 50% cache space is saved. But more interestingly, what we have seen is that across all our experiments, we were within 11% of the optimal throughput that the system could support. So we are very, very close to optimality. And we dug deeper into why we are sometimes this much far away. It turns out that we were not doing intelligent placement for the shards. So if you can place the data shards carefully across your servers, you can actually get rid of this placement thing. But we are sharing the cache very efficiently. The case of transient failures is also very interesting. Here, one of the problems here is that Facebook people told us that 90% of their failures were actually transient. So machines will go away, disappear, but they will come back, right? And to avoid unnecessary data traffic, they actually delay their replica creation by 15 minutes, Facebook people. But what is happening during these 15 minutes is that I have 3 replicas. One replica goes away, so all the queries are now going to the remaining 2 replicas. So the load on these replicas increases tremendously. And we applied Succinct to this problem, and we showed that navigating along this trade-off curve upon load spikes actually provides you a very efficient way by adding and deleting layers to increase the system throughput. And basically, even for 3x load spikes, so the load on one of the replicas increases by 300%. By 200%, Succinct can add a new layer within 5 minutes for uniform workloads, right? In fact, for skewed workloads, Succinct can do it within a minute, as you would imagine, because some of the values in the new layer that have been filled can be reused very frequently. So for skewed workloads, it actually performs much, much better. Okay, so I'm going to skip this. Finally, last 2 minutes I have, I'm going to talk about 2 or 3 interesting problems to give you a flavor of what kind of problems interest me in general. But I think it's a great time to be solving these problems. In particular, we are working with larger and larger scales of data. Users are more and more insatiable, which has led to new challenges and opportunities in this space of distributed systems. One interesting thing that has gotten a lot of my attention in last few months is security and data confidentiality. And I think I'm planning to do a lot more work in this space. In particular, the cloud has given us access to cheap infrastructure, but then we have to upload our data onto the cloud, and customers want some kind of data confidentiality properties. And I don't know what the reason is, but in the last 1 year, we have seen more hardware, more new hardware announcements than ever. In particular, about this new memory technologies, new hardware enclaves, and the entire data center that Facebook designed, which is called the resource disaggregated data center. So let me dive deeper. But looking at a 2-3 year plan, one of the things that I want to work on is apply some of the succinct ideas to graph queries and graph problems. Another one is this problem about doing queries on compressed and encrypted data, and finally this resource disaggregation data center. So let me talk about each of one. Graph store. So a lot of web services today, they exploit user information or user social network information to actually provide personalized query responses. However, this is a very hard problem. Think about this simple query, which is finds all friends of Sid who live in Berkeley. Okay, there are two ways today to do that. A subset of the systems, the way they would do it is they'll find all friends of Sid, and they'll find all people in Berkeley, and they will do a complex join. Right. Now, joins is a problem that we have not resolved so far. It's a completely inefficient solution, especially if Sid has a lot of friends, which is true, and there are a lot of people in Berkeley, which is also true as well. Right. Another way to avoid this complex join is you look at each friends of Sid and check if they live in Berkeley. Okay. What is the problem here? The problem here is that Sid might be hard data, so to say. Right, but friends of Sid, some of the friends of Sid in the social network case might actually be cold data, right? so to say. But some of the friends of Sid might actually correspond to the cold data in the system, right? Which means that even one of these queries going to secondary storage would lead to significant throughput degradation. Essentially, this is one of the known problems in graph queries, that they exhibit very little or no locality, right? So this is a locality problem in graphs. And the intuition is that compression should help, okay? So the second problem is compression and encryption. So there's been a lot of work on interactive queries on compressed data, succinct, and on encrypted data, for example, cryptDB, and some of the work from Microsoft folks as well. So I think this is both important and challenging. People want to achieve the benefits of compression, but they also want to achieve data confidentiality. However, it's an extremely non-trivial problem if you think about it. If you encrypt the data first and then compress, clearly encryption has pseudo-random properties, so you are not going to get enough compression. But if you compress the data first and then encrypt, server loses its ability to query compressed data. So it's unclear that how could you even design a system that can do queries on compressed and encrypted data, right? So are we stuck with using only one of these, either getting benefits of compression or getting the properties of encryption, or can we do something interesting in this space? And we have made some very interesting progress in this, but I think we need fundamentally new techniques to be able to solve this problem. And finally, resource disaggregation data centers. We have been building these servers for many, many years that tightly integrate these small amount of resources. And recently, industry has moved to this new architecture where they're proposing a disaggregated architecture. Essentially, what they say is that we will build a blade of CPUs, blades of memory, and then we'll connect these different blades using network fabric. As you would imagine, this new architecture completely alters the many fundamental assumptions that we made in design of distributed systems. In particular, we don't have high CPU to memory bandwidth or low latency. And what do the failure models look like? How do we exploit data locality if we don't have CPU and memory next to each other, right? And I think there will be a lot of interesting new challenges in this space. So resource disaggregated data centers is one of the big things from the industry side that is happening, at least from Facebook and Intel, and academics are just starting to look into this space. Okay, so what I talked to you about today was the Succinct project, which I spent most of my time with. What I did not get a chance to talk to you about today was this resource disaggregation, some of the recent work that we did in resource disaggregation, and in particular about understanding what the network requirements and systems requirements are in this disaggregated architecture. We actually built a system that you can take today and go to Amazon EC2 and actually emulate resource disaggregated hardware using Amazon EC2 servers. I did my PhD thesis on graph queries. I did not get a chance to talk about some of the results there. What we showed here in my PhD thesis was that using approximation and using graph sparsity as the only assumption, we can actually get significantly better results in the set of design and build some interesting data structures and algorithms for answering some specific set of queries on graphs. And we have been doing some follow-up work recently on this into transforming these into real systems, working with LinkedIn. And I also was involved in one of the early works on network debugging, which started this whole new area about data plane debugging in networks. And I didn't follow up much until recently, and we have started doing some more work because I think the area has gotten too complex and we can build simpler schemes. But this was my work during my PhD as well. And I did some of the works in scalable routing and some coding and information theory work when I used to be younger. I think this kind of summarizes the kind of research flavor I have. And none of this work would have been possible without all the awesome collaborators that I have worked with over the last 2-3 years and some of the older works in the past. So thanks all for coming, and thanks to all the collaborators. That's all I have to say. I can take more questions now.
So the curve where the performance suddenly drops when you start swapping presumably also applies when you go from like the L2 cache to the L3 to the RAM and so forth. Have you seen that?
Yeah, no, we haven't actually. So we have seen while building the system on how to optimize with the L2, L3 caches, but we haven't seen that essentially what we were working with, the data was hundreds of gigabytes of data, right? So in that space, just looking at L1, L2, L3 cache wasn't very interesting.
But if you put in a megabyte of data, does the system operate faster?
Oh yeah, absolutely. That over there, the gains are much faster, because today going to L1, L2, L3 cache would be roughly 30x faster than main memory, right? So your drop would be actually even more significant because OSs also do a lot of optimizations in terms of prefetching and all. But for the kind of workloads that we were working with, which is random access and search indexing style of workloads, you really don't see much benefits by L1, L2, L3 cache anyways, because you're doing a lot of random lookups over some data structures. Even in binary search, for example, over an index, right? It's known to be not unless you actually build algorithms or data structures that are very cache efficient, and there's a lot of work in that space. But my hunch is that the gains there are less significant, so to say. Yeah.
Okay, so we're over time, but we can do questions for one-on-one. Thanks again.
Perfect. Great. Thank you. Thank you all.